This is super easy stuff. Easiest stuff in the chapter by far.
Oh, we see that.
No, this is. The next section is a little harder. Dividing polynomials is a little tougher. Adding, subtracting, multiplying, you already know how to do it. So easy. You've already done it, in fact. It's the same stuff you did with complex numbers. When we add, for example, complex numbers with real parts and imaginary parts, just adding like terms, same deal. Multiplying polynomials, you've already done also. When you FOIL out, in chapter 5, when we FOILed out binomials and came up with quadratic expressions, that's all it is. It's just distribution. So this stuff is very simple. Like I say, 6-4 takes a little more doing. Dividing polynomials is a little longer process, and I'll build in more time for that. But this stuff, it's really not bad. Okay, so first of all, when we're adding and subtracting, now there's two different ways you can do this. I don't want to make too much out of this, though. I don't think you can kind of, whichever one seems best to you, go ahead. If you're adding or subtracting polynomials, if you add them vertically, all that means is you're just going to line up the corresponding parts, the corresponding powers of x, and add them up. Okay? So if I want to take these two, for example, 3x cubed plus 2x squared minus x minus 7, 3x cubed minus 10x squared plus 8. If I'm going to add or subtract these things vertically, the only thing I have to be careful of is I have to make sure I have a column for all of the powers of x that show up in any of the polynomials, right? So in this first one, it looks like we've got an x cubed, an x squared, an x, and a constant. Now, what would have happened? What if I was missing, for example, an x squared term in the first one, but I had one in the second? Yeah, I'd want to leave the blank there, so I could still have a column for those x squareds. So that's all I do, right? If I'm adding them up, I just line up the corresponding parts, the powers of x in their own columns, and add. 3x cubed plus x cubed is how much? 4x cubed, right? 2x squared plus negative 10x squared is negative 8x squared. Negative x plus 0 is just negative x, right? If I only have one term, it doesn't change. And then negative 7 plus 8 is 1. Done. How simple is that? That's adding polynomials. If you wanted to add a whole bunch of them, if I had 4 polynomials to add up, adding them vertically is really simple. Then all I do is I just add more than one term in each column. Okay? Once again, though, if you're going to add vertically, the piece that's easy to forget, that makes it a lot simpler, is if you're going to add them vertically, make sure you have a column for each power of x and the constant. Okay? But it is a good way to do it. I don't have to. I can also just combine terms horizontally. And if you're just doing small polynomials or just 2 of them, maybe you'd rather do this. It's up to you. What about this case here? If I'm going to combine like terms. Okay, I don't really like the way they show this personally. Let's kind of do this one on our own instead. I think this is, you can click through this later if you want to, and if you like that format, that's great, but it seems confusing. What I would just do is, I would just do this. If I want to combine like terms, if I'm going to combine 8x cubed minus 2x cubed, what am I going to get? 6x cubed. Yeah, doesn't that make sense? 8x cubed minus 2x cubed is 6x cubed, and let's get rid of those. Okay. Negative 3x squared minus 6x squared. Yeah. Negative 9x squared. Cross them off. Right? 2x minus negative x. Subtracting a negative is? Positive. Add it. Good. So negative 2x minus, same thing as saying plus x is what?
So x.
Negative x. Right? Negative 2x plus 1x is negative 1x. 9 minus 1? 8. Okay, and we got it.
Maybe this is easier.
Okay.
We just start 6-4.
Adding, same deal, right? Same exact deal. If I'm going to add these things horizontally, I've got, now this time, I've only got one x cubed term, so what do I do? Yeah, it stays the same. Good. 9x cubed, and it's gone. There's no x squared term here, but there is one here.
So it's
Plus 5x.
plus 5x.
Okay,
Plus
negative
10x.
2x plus 12x.
Plus 10x.
1 plus negative 4.
Minus 3.
Negative 3.
That's it.
We got this.
Okay, and there's another example, but more of the same stuff. What about multiplying? Okay, multiplying is also really simple. All you're going to do when you multiply is you're just going to distribute. Now, I do have one hint for you here, though, something that I can't remember if not all books do this, but I think this helps a little bit. If you're going to distribute, why not distribute from the smaller to the bigger? By the smaller, I mean the one with fewer terms. This polynomial has 3 terms, this one only has 2. So rather than distributing 3 times, why not just take each of the terms in the small one and distribute to the big one, right? So for example here, let's go through this. What if I distribute the x? X times negative x squared is negative x cubed. Now we're going to combine this idea with adding vertically, so I want to make sure that I'm going to leave a column for every power of x as we go. X times 2x, 2x squared. So the next column would be the x squared term, so I'll just put it next. X times 4, and then the next column is the x column, and so I didn't have to leave any gaps there, right? But what if there hadn't been an x squared term? Then I would have left room for an x squared when I make the other distribution, right? I want to leave a column for every power of x. Now if I distribute the negative 3, the sign goes with it, right? So negative 3, if I distribute that all the way through, what's negative 3 times negative x squared?
3x squared.
And where do I put it?
Under the square.
There we go. Okay. Negative 3 times positive 2x
Negative 6x.
goes in the x column. Negative 3 times positive 4.
Negative 12.
And then all I have to do now is add them up, right? No big deal. So I get negative x cubed.
5x squared. Negative 2x.
Okay.
So it's
Nothing to it.
It's not real heated.
All right. So that's if you're just going to distribute horizontally. Now, if you choose to, I'll show you something else you can do. You can also multiply polynomials vertically. This is okay. This is just like going back to way back in the day when you were practicing in grade school, multiplying multi-digit numbers. Same concept. If you write these things out, but instead of a hundreds, tens, and ones column for the digits, you've just got a column for x squared, a column for x, and a column for constant in this case. If I line these things up, I can do that same process though. I could multiply the negative 3 all the way through first. And you see it's the same thing, isn't it? It's just distribution. So if I multiply the negative 3 through, 4 times negative 3 is negative 12. Negative 3 times 2x is my negative 6x. Negative 3 times negative x squared, there's my positive 3x squared we got. Multiply the x through. X times 4 is 4x, so I line it up in the x column. X times 2x is 2x squared, so we line it up in the x squared column. And then x times negative x squared is negative x cubed. And then I just add them up, right? Doesn't matter. Whichever one you like best, go just use it. Okay? And then this is what we did before. We can skip this. We just distributed all the way through.
I'm sure this is the
Okay.
lesson.
Yeah, there's not much to it, is there? So multiplying, and what are you going to do here? What's your intuition tell you about if I'm going to multiply 3 polynomials, what do I have to do?
You do the first 2 and then do it to the third.
Yeah, we have to multiply 2 at a time. So I would take 2 of these and expand those out. So if we FOILed the first 2, and when we say FOIL, I mean, you understand FOIL is just distribute. That's all we're doing. When we FOIL, I want you to notice something here. When we FOIL, all we're doing is we're distributing the x first, and then we're distributing the -1. First times first is x squared. Let's see, then we get outside, well, I guess it's a little bit out of order, but same deal. Plus 4x. Then when we distribute the -1, we get our -1x. And then we get our -4. And it doesn't matter the order you add those things up in, right? If we combine like terms, the -x and the 4x, combine to we want to do that first, right? Here's something else I sometimes see people doing. Is you FOIL these out and then distribute the x all the way through. We don't want to do that. Why make more work for ourselves? Why not first? If I can, why not always combine like terms and make a smaller polynomial to deal with, right? Okay, so now if I just distribute the x all the way through, I got it, right? I could multiply the x all the way through, multiply the 3 all the way through. We just did one like that. Okay?
Wow.
Okay, now here is one thing. Here is one thing that I do want you to be aware of, though. This is some stuff that's going to be helpful to you. There's a little bit of memorization in 6.3, and knowing these patterns will save you a ton of time. So, for example, if we're going to do the, and we know these already, by the way. We know these in the opposite order. If I'm going to multiply a plus b times a minus b, that's our conjugate pattern, right? If I multiply a plus b times a minus b, I just get a difference of squares. Now, we did this the hard way back in chapter 5. In section 5.2, you might remember we did that difference of squares pattern, where if we saw something that could be written as a difference of squares, we could factor it into first plus the second times first minus the second, right? It's much easier this way. If I see that I've already got a conjugate pattern, so I got two things, added once and subtracted once, that's a conjugate pattern, right? I got the same a and the same b, but once they're being added, once they're being subtracted. If I multiply those out, I always just get the difference of squares. Okay, and we saw this in 5.4 when we were dealing with multiplying out complex numbers. Remember, we had a little trick that if we had a complex number on the bottom of a fraction, we multiplied by the conjugate, and the reason we did that is so that the cross terms would cancel, right? If I FOIL this out, the O and the I just go away if I multiply conjugates. So foiling conjugates, you really are just fooling them. Just the first times the first plus the last times the last, and that's it. So that's handy, okay? So for example, if we see something like x plus 3 times x minus 3, we know right away it's just x squared plus -9, x squared minus 9.
Easy speech.
Okay? If we square binomials, this is a really important pattern. We're going to know how to square and cube binomials. If I square out a binomial just means a polynomial with two terms, something plus something or something minus something. The pattern is always the same, and you only have to remember one of these. You get two for the price of one. Don't even bother remembering the bottom one. If you remember the top one, that works in both cases, because what if I'm trying to square out something like, say, x minus 7? That's really just x plus -7, isn't it? Mm-hmm. Right? And so if you know the top one, you get the bottom one for free. If I'm squaring out a plus b squared, we always get this pattern. A squared plus 2ab plus b squared. Okay? Now, a couple things you'll notice here. Notice that when we square this thing out, when we expand it, that if I add up the exponents of the a and the b, they always add up to 2. Whatever that value is right there, each term, the exponents always add up to that. In the first term, a gets all the exponential power. A gets the power of 2. In the second term, a gets a 1 and b gets a 1. So the a is getting weaker while the b is getting stronger. And in the last one, the b gets it all, b squared. Okay? The pattern with the coefficients, they're also symmetrical. I get a 1 in the first term and a 1 in the last term, and then a 2 in the middle. Okay, so you can kind of visually sort of just remember how that works. And if you want to remember the bottom one, go ahead, but you don't need it. You don't need it. That one does it all. And I'll show you when we do it. An example with variables and numbers. You don't need the bottom one. Okay, so let's try an example. Oh, and then, sorry, cube of binomial. Okay, and this
Same
last
thing.
one. It's exactly the same thing. You only need one of these two patterns. Just need the top one. And I want you to see here that it's the same thing going on, right? Thank you. Yep. Oh, Courtney, would you mind passing me that? One's for you.
Yeah.
Thank you. It's the same thing going on. Notice that the exponent this time is a 3, right? We're cubing out this binomial, so all the powers in each term have to add up to 3. Same thing happening. Start off, all of the exponential weight is shifted towards the a, so the a gets an a cubed. Each term, as we step through all the terms, the a is going to get weaker by 1 while the b gets stronger by 1. So then we end up with a to the 2, b to the 1, those add up to 3, a to the 1, b to the 2, and finally b cubed. Okay? The coefficients, look at the coefficients, they're symmetrical also. They're always going to be, there shouldn't be any difference. We should be able to go front to back or back to front and see the same pattern of numbers. 1, 3, 3, 1. Okay? All right, so let's try one of these. So what about this guy? It's an x plus 5 cubed. So first thing we want to do is let's write down our pattern. See if you remember the pattern. Without looking, can you tell me what was the quantity a plus b cubed? Okay, good. We're going to get 1 a cubed plus 2, 3. Good. 3 a squared b to the 1, or just b, plus 3 a to the 1 b squared plus, so it went 1, 3, 3, it's got to be a 1.
Plus b cubed.
Okay, good. And now, what is a and what is b in this case? A is
X.
B is
5.
Plug in the pattern. That's it. Right, so we're going to get a cubed is just x cubed plus 3 x squared times 5, right? Everybody see that? 3a squared times b plus 3x times 5 squared, right? Because I got to square the b there, right? Plus b, which is 5 cubed. And now we have to just go back and simplify. Okay, so what do those terms end up being? So this first term is done. That's just x cubed. What about the second one? I want to write the numbers first. So 3 times x squared times 5 is,
15x squared.
yeah, 3 times 5 is 15, so I get plus 15x squared. Next term. 3 times x times 5 squared is 25, right? So how many x's? 3 times x times 25. So 3 times 25 is 75. 75x. And then finally I get 5 cubed, which is just 5 times 5, which is 25, times 5.
125. God, dude. Way to get second grade math. High five.
Okay? Got it?
You and that one.
Questions on that? Does that make sense? Okay. So let's do one with a minus. Okay, so there's what we just did, right? Okay, there's our answer. Okay, let's do one with a minus. So what about this? What if we want to do okay, what about that one?
So 2x is a.
Okay, let's
So the 8 or 2x
screw this down. Okay, let's write our pattern down. So our pattern is a plus b cubed equals
A cubed plus 3A squared plus B
times b.
times B plus 3A plus 4 times B squared plus B cubed.
Okay, so in this one now, what's our a? This is the critical part. What's our a and what's our b? A is 2x. Good, right? 2x. And b is no negative 3. Okay, because subtracting 3 is the same as adding negative 3, right? So b is negative 3. So now let's just go through these one by one and see what we get. So a cubed is going to be the quantity 2x cubed, right? Okay, we'll have to simplify that later. Plus 3 times 2x squared times negative 3. So what's going to be the sign of that second term?
Negative.
It's going to be negative, isn't it? Right? Because I'm going to get some positive stuff times a negative is going to make it negative. Okay? Plus 3 times 2x times negative 3 squared. Now, don't say anything. Everybody look at this. What's going to be the sign of that third term? It's going to be positive, isn't it? Because I get a negative number squared, which makes it positive. Good. Okay, and then finally, plus negative 3 cubed. And what's going to be the sign of that one? Negative. Good. So if we simplify these, then, now, the quantity 2x squared, going back to our work that we did on properties of exponents earlier, what do we have to do there? If I want to cube out 2x, what do I have to do? Good, I got to distribute the power to both parts. So I'm going to get 2 cubed, which is 8 times x cubed. Right?
Yes.
Okay, next one. This one, there's a little more to this one. So I've got to take care of the 2x quantity squared. What's that going to be? 4 times x squared, because I got to square the 2 and the x. Okay, now I got to multiply through by 3 and then by negative 3.
Negative 36x squared.
Oh, good. So 3 times 4 times negative 3 is minus. So I'll change that sign. Minus 36 x squared, right?
How is this easier than just boiling it?
Well, once you get good at this, it's about 10 times faster. But once you do it 5 times, you'll have it. So plus, what about over here? Now I've got negative 3 squared is 9. So what's the easiest way? So 3 times 2 is 6 times 9 is, no, 6 times 9 is,
Wow, you're so
how many x's?
1 x squared.
Just x, right? And then finally I get negative 3 cubed.
Which is negative 20.
Got it. Okay. That's it. Okay. What else?
Second. Okay.
Oh. Isn't that cool?
Okay, I'm going to show you one more thing.
You gotta use your toes.
Okay, I want to show you, this is kind of, I sort of like this. In math, every once in a while, you get some kind of, and you see this a lot, we'll get some kind of a pattern that you can sort of see and understand how it develops that produced all those patterns I just showed you and more. It's called Pascal's triangle. This is
Pascal's what? It's that made in China, huh?
Here's how you make Pascal's triangle. It's very simple. It's just a pattern game. All you do is you're going to start with a 1. You're going to make a triangle, and at the very top is a 1. Down each slope of that mountain or triangle, you're just going to get 1s. So I'm going to have a 1 there. My next row is going to have 2 1s. I'm always going to increase the number of numbers in each row by 1 each time. So I go, my first row has a 1. My second one has a 1 and a 1. My third one is going to have a 1 and something in the middle and a 1 over there. How do I know what's in the middle? The game you play is you just add up whatever goes there. I'm just going to add up each of the 2 numbers that are above it. So 1 plus 1 is 2. Yeah. Okay, next row.
11. One.
Okay, next row is 1 and 1. And then to get the numbers in here, I've got
Four.
to add up.
3.
Oh, there's 3 and 3. Oh,
Do those numbers look familiar? Those were the coefficients, weren't they? 1, 3, 3, 1, 1, 2, 1. And so what's nice about this is, if I wanted to square out a binomial, or if I wanted to multiply out a binomial to a much bigger power, this tells me the pattern that I would use. So if I keep going with this, what's the next row going to be? 1, 4,
1, 4, 6, 4,
4, 1, and then finally we'll stop here.
5, 10, 10, 5.
How would that bottom one be?
One.
Okay, so now let's. What do these rows mean? The first row, we're going to associate a number with each of these. The first one was row. We start with a 0. The second one was a 1. The third one was a 2, 3, 4, 5. And those are just the powers of the binomial, right? So this was the expansion for a plus b squared, right? A plus b squared, if I wanted to fill in the blanks. Remember what we said, a plus b squared was 1a squared plus 2a to the 1 b to the 1 plus 1b squared, right? These are what we've just developed with Pascal's triangle are the coefficients. All you have to do now is just fill in the powers of the variables, but it's the same thing it always was. It starts with all the power in the first variable, or the first term, and it ends with all the power in the second term. And it just kind of steps down from one to the other one in between. So then the second one here was our a plus b cubed, was 1a cubed plus 3a squared b to the 1, right? Plus 3a to the 1 b squared plus 1 b cubed. And so if we wanted to very quickly come up with a formula, because think how long it would take for us if I wanted to FOIL out something over and over and over again. What if I wanted to deal with a plus b to the 5th? That would take a long time. If I had to do that from scratch, I'd have to FOIL 2 of them, get an answer. FOIL another one, distribute another one, get an answer. Distribute another one, get another answer. And then that would take forever. So this is much faster. Now I know these are going to be the coefficients of that row because that's what Pascal's triangle told us. What are the powers going to be? First one is going to be a to the 5th. Yeah, because we know this is row 5, right? Plus 5
A squared.
a to the 4th, b to the 1, plus 10
To the
a cubed b squared plus 10
8 second.
a squared b cubed plus 5
B.
a to the 1 b to the 4th plus 1 b to the 5th, and there's our expansion pattern for that one.
Whoa.
Okay? So you can always,
Decrease the density.
and there is a formula that you don't need the triangle, but I never remember the formula because this always works and it's easier to do. It's just a quick little pattern. Okay? All right,
Simple.
that's good.
You're a genius.
We do like
It's so hard.